Hello everyone. In this video we will be introducing the notion of integration by parts. Okay, so the first question here is, well, why do we care? What are we going to use integration by parts for? So our main integration technique that we've learned so far, besides just the very basic antiderivatives, is the method of substitution. And the way we usually think of this, right, is that this is the reverse chain rule. And so it kind of corresponds over here to the chain rule. Now, it's not going to be true that every integration technique we learn is directly linked to some derivative rule that we have, but it is true in this case. So integration by parts is going to be to the product rule as the method of substitution is to the chain rule. So it's going to give us a whole bunch more functions that we can deal with that we couldn't deal with before. So if we're going to go backwards from the product rule, let's just quickly remember what exactly the product rule is, and I'm going to put it in the notation that we'll use for integration by parts. Okay, so we'll let u and v be functions of x, and so if we take the derivative with respect of the product, uv, then, you may have seen fg before or something, we get, take the derivative of 1, multiply it by the original other one, and then do the opposite, right? So we have u prime v plus uv prime. So this directly leads us in integration by parts. How so? Well, let's take the integral of all of these things, right? So, the two things on the left and right are equivalent, so, well, I should be able to just take the integral of each side. And we know the integral splits over sums, right? So I can write it like this. Well, now on the left-hand side, by the fundamental theorem of calculus, we know that the derivative being inside the integral, well, you take the antiderivative of the derivative, you get back what you started. This is just going to be uv. And then these things, well, they're kind of hard to tear apart, so we'll leave them like this. And now the end result is we will usually see something of the form u dv. dv is just the same thing as v prime here. And similarly, du is the same as u prime. This is just the usual way you'll end up seeing it. So the integral of u dv, well, that is this guy here, right? So how do you get that by itself? You just subtract over. So this is going to be uv minus the integral of v du, or v u prime. Okay, and so this is exactly the rule for integration by parts. Okay, so here's an example. Now we pretty clearly see that we have a product here. Now the question is, what would we like to be u, and what would we like to be our dv? Right, our end result is we want to view this as a u dv first. Well, if one wants to be integrating these things, right, so this ends up being uv minus the integral of v du. Well, we're starting with this, we end with this stuff. This means that we would like dv to be something easy to integrate, right, because we're going to be finding v, and we would like u to be easy to derive, because we need to find du. Right, so if one of those is not true, then it's going to be pretty hard to find the integral of v du. Now in this case, both x and sine x are easy to integrate and easy to derive. So the real question is, what one makes it simpler? Okay, so these are the 3 steps I try to abide by while choosing my u and dv. So in this case, both are easy to do in both directions, but if we integrate or derive sine, we're going to end up with plus or minus cosine, right? So it's kind of the same level of complexity. On the other hand, if we integrate x, we end up with x squared over 2, but its derivative is 1. And that is much easier to deal with. So we would like x to be our u, and sine x dx, right, you need to have all of the remaining stuff be your dv. Well, then we can solve from there, right? So if dv is sine x, then we just go backwards, so v must have been negative cosine, and if u is x, then du is simply dx. Okay, so now I've just kind of substituted in all the stuff we have from up here, and we'll note that, yeah, we have a minus, so this is just plus, and our antiderivative for cosine is sine, right? So we have negative x cosine x plus sine x, and of course we never forget our plus c. Okay, and so this is the whole problem there. All right, so your first exercise is just to solve the integral of x times e to the x dx. Okay, so let's look at another example. So this one's going to be a definite integral, which we'll talk about more in a second. So again, we see two pieces, x and ln of x. So you may think that, okay, last time u as x worked really well, its derivative is 1, life is easy, but then dv would be ln of x dx. Do we know the antiderivative of the natural log? Not yet. So that seems hard. So that should not be our dv, which tells us that u basically has to be the natural log, in which case dv would then be x dx. And then du, of course, would be 1 over x dx, and v would then be x squared over 2. And that would be it. So now I'll just write up the next step. Okay, so you'll notice here the important thing for a definite integral is the thing without the integral on the other side. You do have to evaluate at those endpoints, and this integral carries over the same bounds. Now, to actually do this, note that this inside here on the right integral is really just x over 2, or 1/2 x, which is really easy to integrate. So we actually did simplify things because the derivative of natural log happens to nicely cancel. So we get over here, well, ln of e times e squared over 2, and then the natural log of 1 is 0, and so that's why I just have 0 over here. And then just simplifying, right, we got x over 2, its antiderivative is x squared over 4, and then we'll just quickly evaluate that. And so the natural log of e is 1, so we just get e squared minus 2. Then we have e squared over 4, and of course e squared minus 2 minus e squared minus over 4 is e squared over 4, and then we're adding a fourth, so e squared plus 1 over 4. All right, so here's the second exercise. It's going to be fairly similar to the first one, except for now it's definite, and e to the 6x is just a little bit more complicated than e to the x. Thanks for watching.